Somewhere in the north of Chile, in a building the size of a cathedral, there is a fire that has not gone out in over a decade. Not a fire anyone lit recently. Not a fire that gets relit each morning. A fire that has simply never stopped. Day after day, through every night, every holiday, every storm, every change of crew, every year that has passed outside its walls. Inside it there is a bath of molten metal held at around 1200 degrees. Not warm, not hot in the way an oven is hot. 1200 degrees, hot enough that the metal moves like water, hot enough to glow a color your eyes were never meant to look at directly. And the strangest thing about this fire is not how hot it is. It is that the men who run it are terrified of one thing above all others. They are terrified of it going cold, not exploding, not overheating, not running out of ore. They are afraid of the day someone has to turn it off. Because turning off a copper smelter is one of the most expensive and destructive things you can do to it, and in the worst cases, you never fully get it back. That sounds backwards. A furnace should be safest when it is off. A machine should rest. Everything we own works this way. You turn it off, it cools down, nothing happens. You turn it on again in the morning. That is what off means. For a copper smelter, off is closer to a wound. Tonight we are going to stand inside one of the most hostile industrial spaces that exists anywhere on this planet and work out exactly why. Why a machine built to melt rock is more fragile cold than hot. Why the people who operate it count the years it stays lit like a countdown they are trying not to lose. And why, when one of these does finally go cold, planned or not, the bill can run into the hundreds of millions of dollars and the clock on the whole thing starts again from zero. To understand it, you have to stop thinking of a smelter as a container and start thinking of it as a truce. Let me explain what I mean. The inside of a copper smelter is, by most measures, the most aggressive environment that human beings deliberately build and then stand next to. The molten bath sits somewhere in the range of 1200 to 1600 degrees. It is not still. It moves, it churns, it throws off gas, and it is chemically hungry. Molten slag, the layer of melted rock floating on top of the metal, is corrosive in a way that is hard to picture. It does not just sit in the vessel, it eats the vessel. So the first question any engineer has to answer is not, how do we melt the ore? Melting the ore is easy. The hard question is, what do you make the walls out of if the thing inside wants to dissolve anything you put near it? And here's the uncomfortable answer. There is no material that survives this indefinitely. Nothing you can line the walls with will simply hold forever. Every material we have, every brick, every ceramic, every refractory compound is, on a long enough timeline, food for what is inside. And it is worth being precise about how the slag actually attacks, because it is not simple melting. The molten slag does not just heat the brick until it softens, it reacts with it. Slag is chemically active. It dissolves the compounds in the refractory, pulling them into itself, changing the brick from the surface inward. At the same time, the sheer motion of the bath, the churning and the flow, scrubs at the wall physically, abrading it. And on top of that, the constant swing of conditions inside the furnace, a little hotter, a little cooler, a little more or less slag, puts the wall through endless small thermal cycles even while it is running. Chemical attack, physical erosion, and thermal cycling all working on the same brick at the same time. That is what the lining is standing in. So engineers stopped trying to win that fight outright. Instead, they built the Truce. The walls of a modern smelter are lined with refractory brick, special heat-resistant material that can take the temperature. But brick alone is not enough because the molten bath would still slowly eat through it. So behind the brick, buried in the wall, they put copper coolers, blocks of copper with water running through them in sealed loops, pulling heat out of the wall from behind. Now think about what that does. The cooling pulls heat out of the inner face of the wall, and right at the surface, right where the molten slag touches the lining, the temperature drops just enough that a thin layer of that slag freezes solid against the wall. That frozen layer is the whole secret. It is called the frozen slag, or the skull, and it is a shell of solidified rock that forms on the inside face of the lining. And this shell is what actually protects the furnace. The molten bath is not touching brick. It is touching a frozen crust made of its own material. A scab the furnace grows over its own wound, held in place by the cooling behind it. As long as the cooling keeps running and the furnace stays hot and stable, that frozen layer keeps reforming itself. The bath melts a little of it, the coolers freeze a little more of it back, and in equilibrium holds. The wall survives not because it is tough enough to take the heat, but because a thin skin of frozen slag stands between the metal and the brick, renewing itself every second of every day. That is the truce. Heat on one side, cooling on the other, and a frozen shell balanced on the knife edge between them. And there is a detail inside that truce that is almost too strange to believe when you first hear it. The coolers buried in the wall are made of copper, the same metal the furnace exists to produce. Copper melts at just over 1,000 degrees, and it is sitting inside a wall with a bath on the other side that is hotter than that. By any simple logic, the cooling blocks should melt. They do not, and the reason they do not is the water. The water racing through them carries heat away so fast that the copper never gets the chance to reach its own melting point. The cooler survives only because it is being cooled harder than it is being heated every second without pause. It is a piece of copper kept solid inside a furnace hot enough to melt it, purely by the speed of the water inside it. Stop that water, even for a while, and one of the things protecting the wall is a block of copper that will now start to soften in a place where it absolutely must not. The cooling does not just protect the brick, it protects the very thing doing the cooling. Now you can start to see why cold is the enemy, because that entire arrangement, the frozen shell, the balance, the protection, only exists while the furnace is running. It is a living equilibrium. It depends on movement, on heat, on the cooling water flowing, on temperatures sitting exactly where they should. The moment you disturb that balance, the truce breaks, and the furnace remembers that it is standing in the most corrosive place on earth with no scab left to protect it. Let us walk through what actually happens when one of these cools down, because there are two separate disasters hiding in here, and they come from completely different directions. The first disaster is the lining. When a furnace runs, everything inside it is at temperature. The brick is hot. The steel shell is hot. The copper coolers are hot. Everything has expanded to the size it wants to be, at operating temperature, and it has been sitting at that size, undisturbed, for years. When you cool it down, all of that shrinks. And here is the problem. It does not all shrink at the same rate or at the same time. The interface cools faster than the deep wall. The brick contracts at one rate, the steel at another, the copper at another. Every material in that wall pulls against every other material as it cools, and the frozen slag shell, the protective skull, cracks and falls away from the surface it was clinging to. This is thermal shock, and a refractory lining hates it. Brick that has spent years at a steady temperature does not enjoy being dragged down through hundreds of degrees. It cracks, it spalls, meaning the surface flakes off in sheets. Joints that were sealed open up. The whole carefully built lining, which was perfectly stable while hot, degrades the moment it is forced to change temperature. And then, of course, you have to heat it all back up again to restart, which puts the whole wall through the same violent expansion in the opposite direction. 2 thermal shocks, out and back, for the price of 1 shutdown. The result is that every cooldown ages the lining. Sometimes it takes years off the campaign. Sometimes, if the cooldown is uncontrolled, an emergency, a power failure, something going wrong fast, it damages the lining so badly that the furnace cannot simply be reheated and restarted. It has to be opened up and relined before it can run again. And that word, campaign, is the one we need to sit with, because it is the entire economic engine underneath all of this. In this industry, the continuous run of a furnace between major relines is called a campaign. It is measured not in days or months, but in years. A well-run furnace lining is expected to last on the order of 15 to 20 years of continuous operation before the wall is worn thin enough that it has to be torn out and rebuilt. The very best furnaces in the wider metals industry have pushed past 20 years. One legendary blast furnace in Germany ran for 21 years straight, producing tens of millions of tons of metal before it was finally shut down and relined. That is the number the operators are protecting. That is the countdown. Every day the furnace stays hot and stable is a day added to the campaign. Every unplanned cooldown is potentially years subtracted from it. And the cost of losing that bet is enormous. A major furnace reline in the metals industry is not a maintenance job. It is a construction project. The big blast furnace relines have run into the hundreds of millions of dollars. One project cost over 200 million euros and consumed 7,000 tons of new refractory and more than 2,000 copper cooling plates. Another company spent close to $400 million across 2 relines. Copper smelters are not identical to blast furnaces, but the logic and the scale of the money is the same family. Tearing out and rebuilding the inside of one of these machines is one of the most expensive things a plant ever does. So when an operator looks at that furnace, they are not seeing a machine that melts ore. They are seeing a 15 to 20-year asset with a lining that can only be spent once, and every cooldown draws down the balance early. Keeping it hot is not stubbornness, it is arithmetic. But I promised you 2 disasters, and the lining is only the first one. The second one is stranger, and it lives in the metal itself. Because it turns out that cooling a copper furnace does not just damage the walls. In some furnaces, it ruins the copper you have already made. To see why, you have to understand what these furnaces are actually doing chemically. Producing usable copper is not one step, it is a sequence of steps, and one of the things you are constantly managing is oxygen. Copper and oxygen have a relationship, and it is a fussy one. Take one common type of furnace used in copper production. The shaft furnace, a tall vertical cylinder that melts copper fed in from the top, with burners at the bottom and hot gas rising up through the falling charge. This furnace produces a specific product where the oxygen content has to be controlled inside very narrow limits. A tiny, deliberate amount of oxygen, a few hundred parts per million, actually improves the copper's electrical conductivity, but too much oxygen and the conductivity drops and the properties fall apart. So the whole furnace is tuned to hold oxygen in a narrow band. Now watch what happens when you shut it down. To stop the furnace, you cut the fuel to the burners. But you cannot just let raw molten copper sit there, so you keep air flowing through to solidify the copper safely as it cools. And during that cooldown, while the copper is still hot but no longer being actively managed, it does what hot copper does when air is around it. It absorbs oxygen. By simple diffusion, over the hours of cooling, the metal drinks in far more oxygen than it is ever supposed to contain. And now that copper is contaminated, the metal you had already melted, already spent fuel and time to produce, is no longer usable as it is. Its oxygen content is out of spec. The only thing you can do with it is set it aside and melt it again later, correcting the oxygen the second time around. Think about what that means. You did not just lose the day of the shutdown. You took metal you had already finished and demoted it back to raw feed. You now have to spend the energy to melt it a second time, energy you already spent once, just to undo the damage the cooldown did. Every shutdown converts finished product back into a problem you have to pay to melt again. And there is a reason this oxygen problem is so specific to copper and so unforgiving. With copper, oxygen is not simply a contaminant you want at zero. That would almost be easier, you would just keep all air away. The trouble is that copper actually wants a tiny, precise amount of oxygen in it. That small, deliberate trace is part of what makes the metal do its job, especially where the copper is destined to carry electricity, which is most of where copper goes. So the target is not no oxygen. The target is a narrow window, enough but not too much. And a cooldown does not gently nudge you out of that window. It floods the metal with oxygen far past the top of the range, turning a carefully tuned product into scrap in the space of a few hours, purely because it was left hot in the presence of air with no one managing it. The very fussiness that makes good copper valuable is what makes a spoiled batch so easy to create the moment the process stops. So now you have both disasters standing side by side. Cool the furnace, and the lining cracks and ages, sometimes fatally. Cool the furnace, and the copper inside spoils and has to be reprocessed. One attacks the machine. The other attacks the product, and both of them are triggered by the single act that every other machine we own treats as harmless, turning it off. This is why the whole industry is organized around never doing it, and it goes further than the furnace itself, because the moment you decide a cooldown is unavoidable, a second clock starts, the restart. Bringing one of these machines back from cold is not flipping a switch. It is a slow, careful, expensive reheat, hour by hour, degree by degree, nursing the lining back up through the same temperatures that damaged it on the way down, trying not to shock it again. Studies of large smelters have found that restarting one after it has been idled can cost on the order of 1,000 times more than restarting a conventional power unit. 1,000 times. The startup is so costly that in some parts of the metals industry, there are barely any historical examples of smelters being fully shut down and restarted, simply because almost no one is ever willing to do it. And the reason the reheat is so slow is the same reason the cooldown was so damaging running in reverse. You cannot just relight the burners at full power and drive a cold lining back up to temperature in a day. If you did, you would put the brick through exactly the violent, uneven expansion that cracks it, the inner face racing up while the deep wall lags behind, the whole lining tearing itself apart from the inside. So the reheat has to be nursed, degree by degree, on a controlled schedule that can stretch over days, letting the heat soak evenly through the whole thickness of the wall so that nothing expands faster than anything next to it. The crew bringing a cold furnace back is effectively walking the lining back up the same cliff it fell down, one careful step at a time, hoping the damage from the cooldown was not already too much. And the whole time, they are burning fuel and paying wages to produce nothing at all, because the furnace makes no metal until it is fully back at temperature. A shutdown does not cost you a day. It costs you the cooldown, the damage, the reline risk, the spoiled metal, and then days of expensive reheat producing nothing on the far side. Also, the machine can get back to the exact state it was in before you ever turned it off. So the operators keep it lit through everything. This is the part that changes how you see the whole building. When you understand the truce and the campaign clock and the two disasters waiting in the cold, the strange behavior of the people inside starts to make sense. They run this thing continuously, in 12-hour shifts, around the clock, because the furnace does not recognize nights or weekends. The bath does not cool politely while everyone goes home. It has to be fed, watched, and held in balance without a break, because the balance is the only thing keeping the wall alive. There is always someone there. There is always someone watching the temperatures, watching the cooling water going in and coming out, watching the heat coming through the shell, because a small problem in that cooling system is not a small problem. If the water stops, the frozen shell melts back and the molten bath starts eating the brick directly. They watch the cooling like their lives depend on it, and sometimes they do, because if the corrosive bath burns all the way through the sidewall, the consequences are not just economic. Molten metal at 1,500 degrees finding its way through a failed wall is a catastrophe measured in lives, not dollars. There have been smelter fires and shutdowns caused by exactly this molten metal escaping where it should have been contained. So the vigilance is not paranoia. It is the direct, rational consequence of running a machine whose protection only exists while it is running. To feel how thin the margin really is, follow what an unplanned loss of cooling actually looks like from the inside, not the paperwork version, the real one. The water stops. It might be a pump, a power failure, a blocked line, a leak. Within a short time, the wall behind the brick, which had been held down at a safe temperature by that water, begins to climb. The frozen slag shell, the scab, is the first thing to go. Starved of the cooling that kept it solid, it softens and lets go of the wall, and now the bare refractory is exposed to the full corrosive weight of the molten bath with nothing in between. From that moment, the crew is racing the wall. The bath is now eating brick directly, and brick is finite. Every minute the cooling stays down is refractory that will never come back. If they can restore the water in time, they save the furnace, but still pay for the damage. If they cannot, the corrosive bath keeps burning outward through the sidewall toward the steel shell. And if it reaches the outside, 1,400 or 1,500 degrees of molten metal is now somewhere it was never meant to be. Next to the copper coolers, next to the crew, next to everything. That is not a production incident anymore. That is the scenario every safety system in the building exists to prevent. A burn-through of the sidewall is exactly the kind of event that has caused real smelter fires and forced emergency shutdowns. This is why a leak in a cooling circuit is treated as one of the most serious things that can happen in the plant. It does not announce itself as a catastrophe. It starts as a number drifting on a screen, a cooling water temperature climbing, a heat reading through the shell creeping up, and the people on shift know that a drifting number, left alone, is the first minute of a countdown to a molten breakout, so they do not leave it alone. Ever. Picture the building at 3 in the morning. Outside, the plant is dark and mostly still. Inside, the furnace is exactly as loud, as hot, and as alive as it was at noon, because it has no concept of the hour. A handful of people are on shift. Most of the time, there is nothing dramatic to do, and that is the point. Their job is not to react to disaster. Their job is to make sure the numbers never start moving in the first place, to watch the cooling water temperature hold steady, to watch the heat coming through the shell stay flat, to keep the bath fed and balanced so the frozen shell keeps renewing itself against the wall, invisibly, the way it has every second for over a decade. It is a strange kind of work, being paid to stand next to something enormous and violent and make sure nothing happens. But every one of them knows what the alternative looks like. They know that the calm is not the absence of danger. The calm is the danger, held in balance, and they are the ones holding it. The furnace has been running longer than some of them have worked there. It will, if they do their jobs, still be running long after they leave. None of them will ever see it turned off, and that is the whole idea. And this is where you can step all the way back and see the shape of the whole thing. We tend to think of on as the effortful state and off as the restful one. You work, then you rest. The machine runs, then it stops. Effort is the exception. Stillness is the default you return to. A copper smelter inverts that completely. For a copper smelter, running is the stable state. Running is the equilibrium. The frozen shell holds, the lining survives, the copper stays in spec, the campaign clock ticks forward, and everything is, in its own violent way, at peace. It is only when you stop, when you try to give it the rest that every other machine wants, that everything starts to break. The shell falls away, the brick cracks, the copper spoils, the money burns, and the clock resets. The fire in northern Chile has not gone out in over a decade, not because no one could put it out. Anyone could put it out. It would take an afternoon. It has not gone out because everyone who understands it knows exactly what off would cost. The lining, the metal, the campaign, the restart, and possibly the furnace itself, gone for good. So they keep it lit, not out of habit, not out of tradition, but because they have looked very carefully at what happens when it goes cold and decided that the fire is the safer thing to live next to. The furnace is not a container that holds a fire. It is a fire that is holding itself together. And the people inside are just there to make sure it never has to stop.